Hi everyone, welcome to the fourth lesson for topic 4.1 Forces and Equilibrium. So this is also the last lesson and which we'll discuss about friction. Okay, so something that I just want to point out before we move on to the lesson, right, is that so please always remember that in Mechanics 1, right, the questions that you will be encountered in your exams is not like what you have in your pure maths or in your statistic, which you normally see the cutoff between the chapters like quite obviously. So which means that you can definitely identify this is come out from which chapter and this is from the other one and so on. So even like in statistics, they are overlapping, but the overlapping is always between the two chapters that we already can foresee. Okay, but for mechanics one is pretty hard to do the cutoff because you will realize that there will be a relationship between all the chapters. So, for example, in the previous chapter, we talk about kinematics of motion, right? So, in this chapter, we talk about forces and equilibrium. So, in the next chapter, we are going to discuss the Newton's law of motion. And for that chapter, you will be using what you have learned in the previous chapter and also in this chapter. So that's why I hope that you don't, yeah, like for example, when you try to look at different textbook, right, they try to shuffle all the topics in a different way. They try to rearrange everything. Yeah, that's the, I'm not sure how Cambridge arrange it. Yeah, but that's the idea. So what we are trying to do is you need to make sure that it's not so important that how you cut off the chapter, but it's just that how do you actually relate all the idea together. And if let's say the question require you to actually imagine the situation, then you will need to know which idea that you are using rather than which chapter that you are using. Okay, so yeah, that's the idea. So you realize that a lot of things that you learn in this chapter, actually you will bring it along for the next chapter as well. All right. Okay, so for the learning outcome for this lesson, we are going to talk about what is that meant by contact force. Okay, so which means we'll be learning the normal reaction and also the friction lah. Okay, then we are going to use the model of smooth contact and also what we meant by the rough contact. Then the last one, we are going to discuss the limiting friction. Okay, or what's the state of limiting equilibrium. So the last one is basically about the formula of friction. All right, and what's the terminology that you are going to see in the question. All right, so don't worry, we are going to go through everything to get today together. All right, so let's start with the introduction. All right, the contact force. Okay, so for this part, what we will be discussing is highly related to what we discussed in the previous lesson, which we talk about the Newton's law of motion. So we have like one, two, three, right? So we are going to focus in the third one, which state that for any force that you apply, there will be an equal and opposite force. So if you still remember that idea, okay, so we talk about if you still remember there's an image of a car, right? That if let's say you park a car at the street, so when the car doesn't move, so what happened to the car, then what's the force and so on. All right. So it's the same thing. I'm just going to do a recap here. So when a forces is at rest at a horizontal surface where there's no other forces that acted on it except the weight, right? So we call it as the object is actually in equilibrium. Okay, so it's the same thing also with if the object is moving at a constant velocity, then it's also in equilibrium, right? But we are just going to look at rest for now. Okay, so with what happened is that we know that there will be a weight that actually acted on the surface, right? So this is like the weight from the object. Okay, so because there's always an equal and opposite forces, so that's why we have this force, which is normally called as the normal reaction. Okay, so in this part, we are going to talk about the weight, which is balanced by a contact force. Okay, and we know that this contact force is actually called as the normal reaction. So in this part, you can see that there is a weight, then after that, there's a normal reaction, so there's no friction that involved here. Okay, so let me try to explain a bit about contact force first. Okay, so contact force is basically just the force that actually applied if let's say you have two surfaces that get in contact to each other. So for example, when this object actually get contact with this surface, So the contact force that will be exerted is the normal reaction. Okay, so this is for if the object is at rest. All right, so now we are looking at the part how what happened if, let's say, we try to push or we try to pull the object. All right, so when we try to gently push the object, so you see the object is at rest, right? So when we try to push the object, so which means we are trying to apply a certain force, a certain pull to the object. Am I right? Okay, but because of the Newton's third law of motion that tells us that for every force, there will be a force that is equal and opposite, right? So that's why when we try to push the object will actually produce a force which is equal and also opposite of the force as well. Okay, so for this idea, we can try to look at it as if it's the contact between the object and also the surface that's trying to produce the friction. So which means the friction actually happened here. Am I right? So this is like the friction that oppose the direction of this object. So this is called as the friction. So the friction is trying to prevent the objects from moving, right? So you can realize that except just now we say that there is a weight and then there's a normal reaction. So now we also have the friction. So now when we try to apply the push, there's also a friction that actually occur. So now we have two contact forces now, which is what's stated in your learning outcome, which is the normal component, so which is the normal reaction component, and also the second one, which is the frictional component. Okay, so yeah, for all the examples that we are going to look at, right, you will be actually experiencing how important is to actually identify all the forces that exist in the diagram, and you know how to create your force diagram and so on. Okay, so yeah, for all the contact forces, then you will have the normal component and the frictional component if, let's say, you are trying to push it and so on. So if, let's say, it's just like at rest, there's no other forces, then you have only one contact force, which is called as the normal reaction. Okay, so what happened here is, you can imagine if, let's say, we try to push it lightly, then after that when we try to increase the force, what happened is that because of Newton's third law of motion, so the friction here will actually increase together with the forces that actually increase, right? So for example, when I try to apply 1 Newton of force, then my friction will be 1 Newton. When I try to apply 3 Newton, then now the friction will be 3 Newton as well. But what happened is, you'll realize that when we try to put on more forces, right, what happened is that the object will actually move, right? So what happened at that point is actually when we try to increase the force, there will be a point that the force that you apply is large enough to overcome the friction. So that's why the object will move, right? Because if you imagine, if, let's say, the friction will always increase together with the force, then meaning that everything on this earth wouldn't be moving anymore, because the friction will be like keep on increasing and keep on opposing the push that we are trying to apply. So that's why there will be a point, because we know that when we try to push something, there will certainly be a point that you can actually move the object. So the idea that we are going to look at in this chapter is basically what is the maximum value for the friction. So when we say that our force is large enough to overcome the friction, then what's the maximum value of the friction that when our force exceed that, then the object can move? Okay, so that's the idea. Then what is the factors that actually determine this maximum value? So that's the idea that we are going to look at in this chapter. All right, so now let's try to look at what is that meant by limiting equilibrium. Okay, so when the force on the object is large enough that the object is still in equilibrium. Okay, so yeah, please remember that the object doesn't move yet up. So the object is in equilibrium, but if you try to apply any more forces, that actually you will cause the motion. So this object is said to be in a limiting equilibrium. Okay, so limiting equilibrium is the idea where, I mean, that's like the limit, is where the maximum friction happen. So if your force actually exceed that any more, then forces will happen. So that's the idea for limiting equilibrium. So at this point, right, the friction will always take a fixed and maximum value. Okay, so which means that the friction already reached a certain maximum that it cannot increase together with your force already. So that's why it will actually cause the force, right? So this value of the friction is called the limiting friction. Okay, so for limiting friction, for the frictional force, then we'll always try to write F. So for limiting friction, we will always try to denote it as F limit. So F lim. Okay, it will be equal to mu multiplied with R. Alright, and the mu is the coefficient of friction and R is the normal contact force. Alright, so we're going to discuss about these two variables here. Okay, so this value of limiting friction, I'm sorry, this should be friction. So yeah, I'll try to change it in your notes. Okay, so this value of limiting friction will depends on two factors. So which is what we have mentioned here. So the first one is the coefficient of friction. So which what we denote as mu. Okay, so this coefficient of friction, right, actually tell us how rough the surfaces are. Okay, so which mean as you have a larger mu, which mean that the surface are rough or like it will create more friction than the other. Okay, so the higher the value of the friction, meaning that the more friction that it will actually apply. Okay, so each pair of surfaces has their own value. So for example, when I try to compare the coefficient of friction between the table and the book, it would be different when I try to compare the coefficient of friction between the floor and the book. Okay, so that's the idea. But this kind of value, that's the job of scientists that actually we are not going to look at how do they actually come up the mu. Yeah, but the idea is we know that it tells us how rough the surfaces, and then each of the pair they will have their own value. Okay, so a typical value for mu, it will be between 0.3 and 0.7, but remember that this is like a normal one. So for example, if let's say the surfaces between our table and the book, so meaning if let's say you're having a smooth surface, then then your friction will eventually just be zero. You get what I mean? Then after that, if let's say you have a surfaces which is like the rubber, so you know rubber is going to give you a rubbery surface, so it's very hard for you to like move along the. Yeah, you can imagine compared to a table that's smooth, that's so you can compare for example, like you're having a rubber surface, yeah. So eventually you will actually create more friction from that. So maybe for a surface like that, then you will have a mu that's larger than 0.7. Okay, so this is like just a rough range for you. So you know that if let's say you are getting a number which is like 10 point something, then you might want to check whether your answer is correct or not. Okay, so normally it will just between like 0 point something, or even like I think 1 point something is actually quite high also. Okay, so yeah, that's the idea. Okay, then the second one is it will actually depends on the normal contact force. Okay, so this is the force that we see just now, which is which is on the other direction of your. Oh, okay, I want to explain a little bit about this. Okay, so this normal contact force, right, is acts perpendicular to the surface and the friction. So you might have a question that because of the picture just now, like right in the explanation just now, so we know that this is the weight, then after that, this is the normal reaction. Am I right? So you might have a doubt here is that why don't this formula just write that F limiting friction is equal to mu multiply the weight? Then isn't it is easy? Like why do we want to like create one more which is like the R, then we try to use the R? Okay, so you must remember that the normal contact force isn't always opposite of the weight. Okay, so let me try to give you an example here. If let's say I have a slanted plan, so what happened here is this is my object, right? Okay, So you remember that the weight will always be vertically going downwards. So which means this is my weight. Okay? But normal contact force isn't always opposite of your weight. It will be depending your surface and also where your friction. So for example, this is your surface. So where's the normal contact force? It will be here. Okay, so that's the idea. So when you try to look at this, right, the normal contact force, the R here, wouldn't be equal to the weight here. So that's why you must remember that you cannot take the value of your weight and then you try to take it for your normal contact force, because it will be depending on what situation that you are given. Okay, so that's the idea. But this normal contact force will always perpendicular to the surface lah. Okay, so now we'll be looking at these three situations. Okay, so just now we learned about the limiting friction, right? So the friction can take any value up to its limiting value. So there will always be three situations that will be encountered. Okay, so let's try to do this. So what happened here is I try to push this. Okay, then after that, because the object is going to move to the left hand side, right? Am I right? So that's why the friction will just oppose the push here. So that's why you will have a friction that actually goes like this. Okay, all right, you might have a question that can I try to put my friction here? So the idea is you can. So because when we try to resolve the forces later, right, what is important is we try to look at the direction more than where you label it. So I mean, it's just the same thing when you try to, but the arrow that we try to put is always that where is the push from and is exert on where. So for example here, right, then what we are trying to do is we try to apply the force and on the object. So the forces is actually from the floor to the object. You get what I mean? So that's why normally when we try to draw the force diagram, we will actually draw this more than this. But when you try to actually calculate your force, right, if let's say you are trying to draw it here, it it wouldn't produce any problem as well. It will just be the same thing, because when you try to resolve it, then this will be your left hand side and your right hand side is the same, right? So it's the same thing when F and P is the same, or if let's say you draw your F here, then F and P will be the same as well. Okay, so there's no so much problem on, I mean, where you want to draw it. Yeah, but the idea is you know that it will be opposing the direction where your object is going to move. Okay, it's not your force, it's where your object is going to move. So later when we try to look at the example, you can see the difference between them. Okay, so now this is the three situation that we'll be looking at. So the first one is the object is not about to move. So meaning there's no motion that take place. Okay, so what happened here is you can imagine you are trying to apply a certain push, right? So this force will actually increase according to the push. So that's why when the object is not about to move, which means that the friction is just nice that is equal to the push. Am I right? And this friction will be smaller than the F limit. Okay, because of this friction is less than the limiting friction, so that's why the object is not going to move lah, if let's say the friction and the force applied is the same. Okay, so now the second one that we are going to look at is limiting equilibrium, like what we mentioned just now. Okay, so at this point, what happened here is that your friction will be still the same with your push. Am I right? According to Newton's third law. Okay, so you apply a certain force, then the friction will react the same. But then at this point where there is a limiting equilibrium, so meaning that your friction already reaches its maximum, right? So that's why here your friction is actually equal to your limiting friction. So meaning that the force that you're trying to apply here is the same with the limiting friction. So that's why we say that the object is in limiting equilibrium. Okay, so it's the same thing. Yeah, here I want you to write down yourself so you can remember it. It's the same thing when we try to write the object is about to move. Okay, so which means just a slight force that you're trying to add, then after that, this object will start to move already. Or the other word that they'll try to use is about to sleep. It's not the sleeping, is sleep. Okay, SLIP. Alright, so yeah, when you're trying to look at all this term, then you know that the force that you are applying is equal to the friction, where the friction is basically the limiting friction. Okay, so these two scenario actually give you the same thing. No, it's not like the same thing. It's that the object is at rest. Am I right? So for this two situation, the object is not moving yet. It's just that either it doesn't. I mean, you don't expect it to move, or like slightly more, slightly a slight force that you apply, then is going to cause the force. Is going to force. Cause the motion. So that's why this object is actually still at rest, right? So if let's say they are at rest, so which means this is equilibrium. So that's why you must remember that when we say that the object is in equilibrium, it actually means that the F is less than or equal to the F limit, because we doesn't know that it's not about to move or it's about to move. Okay, so that's why these two are made up idea for is in equilibrium. Okay, so the last one is, how about if let's say the object is moving already? Okay, if the object is moving already, what happened is that we know that the push is actually greater than the friction. Am I right? Because if the friction is, I mean, if F and P is still the same, which means that there's no extra force that actually can cause the motion. So when the push is greater than the friction, then the object will start to move. But at this point, right, what do you think is the relationship between the F and the F limit? Yeah. So when we talk about the F limit, right, which means it's the maximum value of the friction that these surfaces can take. So that's why at this point, your friction is still equal to your F limit. It's just that your force already exceed this limiting friction. So that's why the object is moving. Okay. So yeah, I want you to remember the idea where's the time that which one is greater than which one is smaller than which one. So I mean for the friction, you know that the friction can only take up any value up to its limiting value. So your friction cannot be more than your limiting friction one, because your limiting friction is your max value already. So once your friction already reaches the its limiting friction, then the force that you are trying to apply on that object, there will not be any extra friction that you can add up to balance up the force already. So that's why the object is moving. Okay, so that's the three ideas. So in this chapter, all the example that we'll be looking at will be only these two lah. Yeah, because like what I say, for all the moving part which we try to apply things like F equals to ma or the Subak formula thing, we are only going to look at it in the next chapter. Okay, which like you apply a force, then after that the object move. Okay, so yeah, some notes here is that the friction will always oppose the direction which the object is trying to move towards. So that's why it's important to understand that what is the motion that you are trying to apply, and what is the no sorry it's important for you to imagine where is the object is moving towards. So for example, let me give you a simple example here is that if let's say I have this slender plan lah. Okay, so this is my object. Okay, so you see, right, what happened here is that when I try to apply a certain force, maybe I try to apply here. Okay, so this is like a pull. Okay, so my question to you is, do you think the friction is going to be this direction or this direction? The idea is that both can happen. So why is that? So it's because of it will be depending on what's your motive when you try to pull this object. So it will be the first case. If let's say the object is actually going to slip downwards. So when this object is trying to slip downwards, right, then you are trying to pull it. So that's why the direction of this object is actually going to slip downwards. So that's why the friction is going to be going up. Okay, so that's the first idea. The second one is that the object is not slipping down. So what happened is I want to pull it up. So when I try to pull it up, then the motion of the object is now going this way. So my friction will be going that way. Okay, So it's important for you to understand that why do you apply the force? What do you want to see for the object? Like where is the direction? So that's why you can draw the friction. Okay, so later when you try to look at the example, then you will have a better idea on this. Okay, so yeah, the thing that we mentioned just now is that when there's a there's a friction between two surfaces, this contact is called as rough. Okay, so when there's no surface, then we'll call the contact as the smooth one. Alright, and majority of today's example it will be on rough lah, because smooth, which means you don't have any friction, then you don't need to do any limiting friction as well. Okay, so we'll be looking at two very simple example just for you to understand the idea. Then after that, we'll be looking at four partial questions, like from an easier one, then after that to the harder one. So I hopefully all this example can help you to solve your exercise. Alright, so let's move on to example one. Alright, example one. A brick of 2 kg is at rest on a rough horizontal surface. So the coefficient of the friction between the brick and the surface is 0.9. So calculate the frictional force acted on the brick when a horizontal force X, okay, is applied to the brick, and the magnitude is given in the part ABC here. Alright, so yeah, so let's start with actually write down all the force that act on this brick first. So we know that there will be a weight, right? So the weight here will be equal to the mass multiplied by the gravitational acceleration, so which will give us 20 Newton. Okay, then after that we have our R, so our normal reaction forces. Then after that, if let's say the direction of the motion is going towards x, so that's why our friction will be opposing the direction. All right, so that's all the force that we have here. Okay, so now we need to calculate the frictional force that acts on this brick, right? So which means in this point that, okay, let's try to find out the limiting friction first. Then after that, perhaps we can try to write down for a different scenario what's the motion or how's the motion of the brick here. Okay, so the friction here. All right, don't worry. This is just a question for you to understand what is that meant by the friction and the limiting friction. So you won't be having like this kind of easy question so-called in your real exam. So this is for your understanding only. Okay, so for the limiting friction, okay, it will be equal to mu multiply the R, right? So in this case, we have our mu is 0.9 as given in the question. Then after that, our R here, because it's just opposite of our weight, so there's no other force that actually acts in different direction. So that's why when we try to resolve it, it's just that horizontal we have F and X, then vertical we have R and W. So that's why your R is basically equal to your W, which is 20. So multiply by 20, and we can get our limiting friction in this question is 18 Newton. Okay, so when we try to look at A, right, which means now the horizontal forces X here is equal to 10. So when my horizontal forces here X is equal to 10, so which means that the friction will be equal and opposite of that, right? So that's why my force for my friction is actually 10 as well. Okay, so this number is actually lesser than my F limit. So that's why we know that the object wouldn't move. Okay, so for this part, it's no motion. After that, when we try to look at B, then you can see the force applied here is 18 Newton. So that's why the friction here will be 18 also, right? Then the maximum value that it can take is 18. So that's why your F can be 18. So this is a number that is equal to your limiting friction. So that's why what happened to this brake is actually about to move. Okay? So this is like the limiting equilibrium state. So about to move. All right, and what happened to the last one, C, is that our force applied here is 35 Newton. Okay, so what do you think is the friction? Yeah, so 35, right? So that's why the friction is always equal to the force, but at this place, your 35 is already more than the maximum friction that we can that it can actually produce. So that's why the F here is just still 18 Newton. Okay, because it cannot be more than that. So in this case, which we have our force is actually more than the F already. So that's why it's actually moving. Okay, so that's the idea. So I hope that you can see like how the whole friction works here. Okay, so number two. Okay, a box of mass 5 kg is at rest on horizontal ground. Alright, so we have this horizontal ground. Okay, so we have the box of mass 5 kg, right? So that's why we know that we have the weight. Okay, is equal to 5 times 10, so 50 Newton. Okay, so a box is being pulled by a horizontal force of 8 Newton, so that's why perhaps we try to pull it here. Okay, so the force is 8 Newton, so find the total contact force. Okay, so if you can remember, the contact force actually consisted of your normal reaction and also your friction. Okay, so this is the same thing like number one. So basically everything is quite clear. You only have like the vertical component and the horizontal component. There's nothing that you need to resolve, right? So that's why the weight here is basically the normal reaction here. Okay, so the normal reaction will just equal to the weight, okay, which is equal to 50. Then after that, we have our friction force, which is going to be opposed the direction where you want to pull, or where the object is actually pulling towards your right hand side. So that's why the frictional will go into the left hand side. So as well at this place, the P, yeah, since it's not going to give us anything about the limiting friction, right? So that's why we are just going to just assume that because it's still at rest. So that's why we assume that this force is not actually more than the frictional force yet. So that's why the friction here is actually equal to the horizontal force that you apply, which is 8 Newton. Okay, so for us to calculate the contact force, it will be just the same like how we find the resultant force. So we have, this is like our R, right? Then after that, we have, this is our friction. So that's why our total contact force will be over here. So how do we get this? It's just Pythagoras theorem. Okay, so the contact force is actually equal to Pythagoras theorem. So we have 50 square plus 8 square, and that gives us the answer of 50.6, oops, 50.6 Newton in SF. Okay, so I think this is pretty easy. It's for your understanding that contact force is consisted of two force, which is the normal component and also the frictional component. Alright, so now we'll be looking at the past year question, which we're dealing more with the coefficient of friction, the limiting friction part. Alright, so let's try to look at number 3. Alright, number 3, a block is pushed along a horizontal floor. Alright, so this is a force of magnitude 50 Newton that acts at an angle of 20 degree to the horizontal. Okay, so the coefficient friction of between the block and the floor is 0.3. So this is the mu. So we know that later we'll be using our F, the limiting friction here. So given that the speed of the block is constant, so this sentence actually tells us that the block is in equilibrium. So that's why if let's say it's an equilibrium, our friction that produced here is going to equal to our limiting friction, which is mu multiplied by R. Okay, so after that, then what we can try to do is we can try to label all the force that apply on this block in the diagram. So we know that there's a weight, right? So the weight will be equal to mg. So in this case, we are not given the mass. So instead, we need to find the mass. So that's why we can just write mg. So since g is 10, so it's going to be 10 m. Okay, then after that, what else do we have? So since there's a weight, right? So you remember contact force, there's two. So the first one is going to be the R. Okay, so for in this case, our R wouldn't be the same with our W here because we have the 15 Newton. So later we need to resolve the 15 Newton in the vertical component, and it's going to make some difference in your equation for your between your R and W, right? So that's why the R is not weight in this question. All right, then after that we have the friction force. So we can see that the block is being pushed. Then this block is, I mean, our motive of this push is actually to cause the block to move in the left hand side direction. So that's why the friction will be opposing the direction, right? So that's why we have the friction over the other side. Okay, so that's the idea. So yeah, I don't think there's other force anymore. Okay, so now what we can try to do is we need to do our resolving of the force. Okay, so let's start with our the vertical one perhaps. Okay, so we have R and then W. So the frictional force is not involved in our first equation, right? Because it's perpendicular to the vertical component. So that's why resolving in the direction of Y. All right, so what we have is moving down, we have the 50 Newton and the W here. So that's why it will be W, and then plus moving down, we have 50 sine 20. Okay, all right. So in this question, right, you might be very careful that you see every time when we try to have all the resolving question that we have before, right? If let's say they try to do this, sometimes they try to draw this. So it will be easy for you to understand that when you try to resolve this, then it's going down. Okay, so you must remember that what we are trying to look at is the arrow instead of like the direction that they are drawing. So I mean, although they are drawing in this direction, it didn't mean that when you try to resolve it, it become going up. You get what I mean? So this is just the idea for you to, this is a force that apply on this thing. So that's why when you try to resolve it, this, okay, so you see, right, this is the direction of your force. So after you resolve it, it should be going left and it should be going down. So it's not because of this force is on your right hand side and it's on your upper desk. So when you try to resolve it, you take it as right hand side and going up. Okay, so you must remember to check your arrow there. Okay, so that's the part. So that's why you can see the it's moving down. So when you try to resolve it, it's actually add on the weight here. Then after that, it will be equal to our R. Okay, so this is our first equation. Then perhaps we can try to change our mg here if you want. So 10m, let's try to write our r in front maybe. So r will be equal to 10m plus 50 sine 20. And we can't solve it, yeah, because we have two equations here. So this is our equation 1. Then after that, let's try to resolve in the component of x, sorry, in the horizontal direction. Okay, so what we have is the force here is going right, then we do not have other forces that going right anymore. So F will be equal to, so this thing is going to the left hand side, so it's 50 cos 20. Okay, I think for this question we can straight away solve it already. So our force here is our friction, right? So our friction here is actually equal to mu r. So mu r will be equal to 50 cos 20. And it's given in this question that the coefficient of the friction is 0.3. Okay, or we can actually write here 0.3 r. Alright, then after that, when we try to solve this, then we can try to straight away write it here. So 0.3 r. Okay, so after we do this, then I think for this part we can actually solve it. Then we can get our r is actually equal to 50 cos 20 and then divide by 0.3. Okay, so after you get the answer, please always make sure that you save your answer because in this question, or else you can try to leave your answer 0.3 over here. So when you try to substitute in your number 1 equation, then you can, I mean, you can straight away put the whole thing over here, then you can find your m. Okay, so that's the idea. So then after that, we can try to substitute, then go back to our first equation. Okay, to get our answer. So 156, remember to keep your value in your calculator, 10m plus 50 sine 20. Okay, so after you get this, then we can try to solve 1 minus 50 sine 20, then divide by 10. Okay, so I'll be able to get my answer is 13.95144 and so on. Okay, so when I try to make it to three significant figure, then it will be 1.40. Sorry, 14.0. What am I doing? Yeah, so 14.0, and that's my mass, right? Okay, so this is my mass, so it's in kg. Alright, so that's the idea how you solve it. So what's important is you know how to label all the force, then actually it's just by resolving your forces, then you can get your answer. Okay, so now let's move on to number 4. Alright, number 4, a small ring P of a mass 0.03 kg is threaded on a rough vertical rod. Okay, so this sentence is to tell us that there will be a friction actually between the ring here and also the rod here because it's a rough rod. Okay, so yeah, then a light inextensible string is attached to the ring and is pulled towards an angle of 15 degrees to the horizontal. So this is the tension of the string. So the ring is in limiting equilibrium and on the point of sliding up the road. Okay, so let's try to, and the question one is to find the coefficient of the friction. So what we can try to do is let us try to write down what's some force that actually apply on the part where there's the ring here. Okay, so this ring has a mass here, right? So there's a weight and it will be equal to 0.3 Newton. Okay, then after that, this is a tension that is been given here. Then the tension of the string is 2.5. So the ring is in limiting equilibrium and on the point of sliding up. So that's why when I try to apply this force, we foresee that the direction of this ring is sliding upwards. So that's why we have a force of friction that's opposing the moving upwards, which is moving downwards here, the friction. Okay, and don't forget we also have the normal reaction because this thing is moving towards, so you can imagine that when you try to resolve the 2.5, right, it should be moving to the right hand side. So there should be another force that trying to balance up the element that you have to the right hand side. So that's why you have a normal reaction here. Okay, and you see this normal reaction will be always perpendicular to where your surface is. All right, so that's the idea. So now we can try to find out what's the thing that we have here. Okay, so since it's in limiting equilibrium, right, so that's why all the friction that actually exert here is the limiting friction, which will be equal to the mu r. So in this case, we have two variables here, which is our mu and our r, right? So let's try to find out whether we can actually do solve for one variable first. So I think it's quite obvious that we have this part is going to be 2.5 cos 15, right? After that, this moving upwards, we only have this force that needs to resolve. So 2.5 sine 15. Okay, so if let's say we try to solve this one first, then if in the friction then we have mu and r, so we have two variable. But if let's say we try to resolve horizontally first, then we have only r here, then I think we can try to solve the r first. Okay, so resolving it in a horizontal component, so what we have is our moving to the left hand side is equal to the right hand side, which is 2.5 cos 15. So from here, then we can actually solve our normal reaction already, which is 2.415. So remember to keep this value in your calculator, yeah? Okay, so after you get this, then now we can resolve it to the vertical component. So what we have is moving up, we have 2.5 sine 15, then it will be equal to moving down. We have the weight, which is 0.3, and then plus the friction that we have here, right? So we can write friction or you can straight away mu r. All right, then let's substitute our r in this equation. So 2.5 sine 15 is equal to 0.3 plus mu 2.415 then mu. Okay, then after that, now we can actually use our calculator to solve it and you'll be able to get mu is equal to 0.144 in 3SF. So mu is just a coefficient, so that's why you do not have any unit for that. Okay, so yeah, this question is only 4 marks. So basically, it's just a very straightforward question, and it's for you to actually you know how to label the force diagram, then you will be able to actually solve it already. Okay, so number 1 and 2 is easy in a form where it's basically for this is like a vertical one. So when you try to resolve it in the vertical component or in the horizontal component, right, it's not going to be very complicated yet. So for the next two questions, we are going to look at the slanted plane. So that's why it will be a bit it's not very hard, but the idea is you're kind of is a bit complicated. I mean the element that you have is much more when you're trying to do your resolving. Okay, so let's try to look at number 5. All right, number 5, a particle of mass 12 kg is on a rough plane inclined at an angle of 25 degree to the horizontal. Okay, so which means we might need to draw ourselves here. Okay, so we have this horizontal plane. Sorry, we have this rough plane, right, inclined at an angle of 25. It's a bit, let me try to redraw it. Okay, so this side and this side. So we know that this is 25 degree. So we have this particle of a mass of 12 kg. So we can try to put like this. Okay, so this is the 12 kg. So it create a weight of 12, 120 Newton, right? Okay, then after that, a force of magnitude P acts on the particle. So this force is horizontal and the particle is on the point of moving up. So that's why you can, I mean, that's only two idea that how you want to act the force, right? It's either like you put it here, so it acts on like this, or it acts on like this. But the question said that the force is applied and the particle is on the point moving up. So that's why the horizontal force will actually looks like this. Okay, so it's like so that it's on the point of moving up, right? So this is the magnitude of P. Okay, so the coefficient of the friction of the particle and the plane is 0.8, and the question wants to find the P. Okay, so let's try to write down all the forces that we have in this question first. So from here, then we will have a normal reaction as well, right? It's acting up here. So this is our R. So since that the particle is on the point moving up, so that's why the friction will be moving down. Okay, so this is our F. And since the question tells us that they are inclined, so it's on the point of moving up. So that's why our force of friction here is just equal to the limiting friction, okay, which is equal to mu r. And the question already gives us that the mu is 0.8, so that's why it's 0.8 r. So we can straight away use this value later. Okay, so you actually have two situations where how you want to resolve your force. So as we know that the first one is you can resolve it in the direction of the plane, right? Then the second one that you can try to do is you just continue to resolve it in the horizontal and the vertical. So in this question, I don't think there's much difference because whenever which direction that you are using, at the end you still need to resolve two. I mean, for example, if let's say you want to use parallel to the plane, right? Then you have F and R. Okay, so which means you will need to resolve W and you need to resolve P. Then after that, if let's say you are doing a vertical one, then you need to resolve R and you need to resolve F. So what we can try to do is you can try to see what's the thing that we can try to find first, which is the one that actually allow you to solve it in an easier way. So in this case, then we can try to, this is 25, right? So by using a Z, then this is how I can get this is 25. Oops, I'm sorry, Z. So yeah, this is 25. All right, so this is the Z thing. Okay, then after that, same thing here. So which mean that if let's say this and this is 90 degree, right, then we can get that here to here is going to be 65. Okay, so let's try to do maybe resolving to the plan direction first. Okay, so resolve to the direction of the plan. Okay, so what we have here is on the plan, so we have P, then it's going to be P cos 25. Okay, it will be equal to you have over here. So the weight will be moving to right left hand side as well. So that's why W and F should put together. So you only have P cos 25 then equal to the force and then plus the resolving for the for the weight here. So that's why we need to find the angle here as well. So this is 90. So that's why this is 25. So this is 65. Okay, so when you try to resolve to that direction, then it will be W cos 65. Alright, so W cos 65. So we can try to straight away change our R here. So we can get P cos 25 is equal to 0.8 R, and then plus our W is 120, and then cos 65. Okay, so we have our P and R, so we can't solve it, so we can just leave our answer here first. So this is our number one. Okay, then after that, let's move on to the two. So resolving perpendicular to the plan. So what we have is, this is the R that going up, so there's only one force that going up, so that's why it's R is equal to, what we have here is going down, then we have our weight here, right? Then also our P here. So the P here then is going to be P cos 65, or you want to do P sine 25 also can. So P sine 25, and then plus the weight moving down, so is W sine 65. Okay, again, I hope that you are not looking at where the force is, you are looking at the arrow. So that's why moving down, then you have the weight is moving down, the P is also moving down. So that's why you are not resolving the P and R together, because R is not, the P is not moving like this. So it's not, I mean, it's not resolving to the upper part and also the left hand side. It's actually right hand side and also downwards. Okay, so that's the part that you might be need to a little bit you might need to be a little bit careful when you try to solve this. So same thing here, then we can try to substitute our W here. So we have R is equal to P sine 25, then plus 120 sine 65. Okay, so since we have these two, then now we can try to substitute our R, I think. So use number 2, substitute into number 1. So P cos 25 is equal to 0.8 P sine 25 plus 120 sine 65, then plus 120 cos 65. Okay, so yeah, I think you should be quite familiar with this kind of equation already. So you can try to just bring our P to another side. So P cos 25 minus 0.8 sine 25. So what we left here is 0.8 times 120, that gives us 96 sine 65, and then plus 120 cos 65. Okay, so from here we can solve our P. Alright, and you should be able to get your P is equal to 242 Newton to 3 significant figure. Okay, so I think this is quite straightforward. Yeah, I mean, depends on you how you want to do it, but in this question, they only want us to find P, right? So that's why you can straight away use your equation then solve your P, and the question didn't ask us to find our R. So that's why you can just ignore, I mean, you do not need to continue to solve your R over there. Okay, so the other thing that maybe you can try to write here is that the how if let's say you resolve it in horizontal or vertical. Okay, so I'll just write down, or okay, so this is the part. If let's say you want to resolve horizontally and vertically, it's just the same. So let's try to resolve it in the x direction first. Okay, maybe I try to use another color so not to be that confusing. Okay, so if let's say you try to resolve it in the form of uh component of x. Okay, so we have going to the right hand side, then we have our P, right? So it's going to be P then equal to this one. So you need to see that R is moving towards left hand side as well, and the force here. So when you try to expand this, okay, so this line and this line, so that's why this is 25, so this is going to be 25 as well when you try to look at it like this. Okay, so that's why P will be equal to your R cos 65 then after that plus your F cos 25. Okay, so this is your first equation also. Then after that, your second one, when you try to resolve it in your y direction, then you have your moving down, you have your W and your F. So that's why it will be W plus, so F here moving down, it will be F sine 65, oh sorry, F sine 25. Okay, and then going to be equal to, moving up you have only r, but then you need to resolve it, so which means here, so this is 90 degree as well, so this is 65, and then you have r sine 65. Okay, so this is another idea. If let's say you want to do it, then it will be just the same lah. You substitute your mu r here, then you substitute your w here. Then at the end, you're just going to get the exactly same answer like what we did at the front part here. Okay, so that's the idea for this question. So I hope that you can get the idea. So the what is important is the force diagram, and also you are not confusing with, you are not looking at, because of this line is at here, so that's why you resolve it, go to that direction. But the idea that is that it's depending on the arrow. So it's a force that acts like this, so that's why when you resolve it, it should be going down and going this way. It's not because of this thing, so that's why the line is here, so that's why you resolve it here and here. It's a total different, it's a wrong idea there. Okay, so that's the part. All right, so now we'll be looking at the next part, which I'll show you like the difference between the friction, the different motion that's trying to that's trying to change where your friction is. Okay, so let's have a look at number 6. All right, number 6, a particle of mass 2.5 kg. So this is the particle. All right, then we can try to write down mass 2.5. So which means we have the weight here, right? That's the vertical component that moving vertically downwards. Okay, so the mass is 2.5, so the weight is 25. And then it's on this rough plane that incline at 20 degree, right? So this particle is held in equilibrium by the force magnitude T here, making an angle of 60 degree towards this plane. Okay, so the coefficient of friction between the particle and the plane is 0.3. So this is the mu that we are going to use it later. So question 1 is to find the greatest and the least possible value of T. Okay, what does that mean? Okay, let us try to just put down the other forces that we have here first. So for example, this is a plane, right? So the normal reaction will be perpendicular to the plane. So we have this line, okay, which this is our normal reaction. Okay, so you can see that in this question, the question didn't tell us that whether this line is trying to pulling the particle moving upwards, or is trying to prevent the particle from slipping downwards. Okay, so it's two different idea, because you are going to label the friction in different direction. So that's why this question is asking you for the greatest and the least. So which means later when we trying to do our friction, right, we'll need to do two. Okay, so now let's try to label the what is that, some of the important angles that we have first. So if this is a horizontal line, then I'll have my horizontal line here as well. So this is 20, so that's why this is going to be 20. So you should be able to know that 20 and 60 isn't make a 90 degree, right? So that's why the tension here is not is not perpendicular to the horizontal one. So that's why the vertical line should look like this. Okay, which this place will give you a 10 degree. Okay, so since R is perpendicular to the plane, right? So that's why this is 60, this is 10, and this is going to be 20 as well. All right. So now we can try to look at the friction part. So yeah, you can listen to me carefully. So the first one is we consider the part which gives us the least possible value. So this, because the question tells us that the particle is held in equilibrium, right? So that's why there's no motion happen there. Okay, so the least possible value for my the least possible force that I try to apply here is actually trying to prevent this particle from sliding down the slope. So that's why I'm trying to prevent it sliding down the slope. So that's why my friction will be going up. So that's the idea for the minimum tension. Is that okay? Okay, so now the second part is for the maximum part. So for the greatest T, right, is that this force is already providing the maximum force, but it's still not enough for you to actually make the particle sliding up the slope. So that's why the friction is opposite of the motion of sliding up. So that's why the friction is sliding down. So this is the two different idea, which this one will give you the minimum tension and this one will give you the maximum tension. Sorry, my tension here as if the T. Okay, so that's the idea where what we want to find. So basically the difference between the equation is just that one, the friction is moving towards the other side, the other one, the friction is moving the other side. Okay, so you can imagine that there will be three equations that involve in this question. So we can try to see where is a good direction for us to actually resolve our force. So you can imagine that if let's say I want to do vertical and sorry, I want to do horizontal and vertical, right? Then how many force that I need to resolve? I need to resolve my F, I need to resolve my T, and I also need to resolve my R. So if I were to resolve it along the direction of the plane, then I only need to resolve my W and I also need to resolve my T. So that's why an easier approach in this question is to resolve it along this plane. Okay, so let's try to form our first equation first, which is the equation without F first, which is the when we try to resolve it perpendicular to our plane. Okay, yeah, so just a notes for you is that I mean for this part, right, when you try to look at the marking T, you should realize that they normally don't write this part. It's just that they try to write it in the notes part, right? It's not something that compulsory for you to write. So this is for your reference that you understand where you are resolving to. Then later when you, I mean, especially you want to check your answer, then you know that where to check. Okay, so what they are trying to check from is just that the equation that you form, then they will actually know that where is the direction that you are resolving it. Okay, all right, so resolve to the direction perpendicular to the plane, then I have, what do I have? So I can imagine that I will have this going up, I have my R and also I have my T, right? So R is going up together with my T force is also going up, so I can do T. It's either you can do cos 30 or you can do sine 60. Okay, and it will be equal to, so don't forget this is the direction of the W, so we are going to solve for our resolve our W here. So where's the direction of this? So we try to draw a line going down. Okay, so this vertical line is this dotted line, right? Then this dotted line is this R line, so that's why it's something like this. So this is 20 and also this will be 20 as well. So this is 20. So for me to resolve it in the vertical, then it will be 25 cos 20. Okay, or we can write W first. So W cos 20. Okay, so now we can try to substitute some value that we have. For example, the 25 here, other than that, I don't think we have. So we try to make our R as our object perhaps. So R is equal to 25 cos 20 and then minus 10t sine 60. Sorry, I keep on mentioning like the tension. Okay, so this is our first equation then. So now let's try to look at the second one, which I'll try to use the other color, which is if let's say that provide us the minimum force, the minimum T here, so that we are trying to preventing it to sloping down, so to slipping down. So that's why we have like the friction is going up. Okay, so we try to resolve it in the direction of X. So before that, we can try to write down our F first maybe. So our friction here is equal to our limiting friction, okay, which is equal to mu r, which mu is given is 0.3, then multiply I r. Okay, so after we get this, then now let's try to resolve it to the direction of r. So this is my second equation here. So I have towards this direction, then I have my tension, I have my T here, and also I have my friction. So that's why it's going to be T cos 60, T cos 60 and also F. So that's why I can just write f. So t cos 60 plus f, then it will be equal to, what do I have towards my right hand side? Is that going down? So I have the weight, right? So this is perpendicular, so I do not have any r component. So my w is going to be w sine 20. Okay, so let's try to substitute some of the unknowns that we have here. Then we try to bring the f to the other side, I think. So t cos 60, then it will be equal to w is 25 sine 20, and then minus the f that we find just now is 0.3r. So this is another equation. So now we try to look at, if let's say it's the purple color for this one. So it's the maximum force that actually try to apply, which is the T here. And what we try to do is actually trying to make the particle slide up the slope. So that's why the friction is moving downwards. Okay, so what we have here is that towards this direction, then now we only have our T log. So which means this is another Rx. So T cos 60, then the F now is in the same direction with W sine 20 already. So that's why I have W sine 20 plus F. Okay, so let me try to rearrange it to get the same thing. So I have T cos 60 equal to 25 sine 20 and then plus 0.3r. So you can see the difference between these two equations, right, is just that one is plus and then one is minus. Okay, so it will be depends on you whether you would like it to combine this or not. So if let's say you don't want to combine, it's just the same thing. So you use this to solve with this one, you get one answer. Then after you get the answer, right, then it's the same thing. You try to use this one and this one. Okay, so let me write down. So this is my first equation, right? Then I have my second equation. I have my third equation. So which means that it will be depends on you. This question wants us to find our t. So which means you can use your first one and use your second one. Then after that, you get your one value of t. Then after that, you're going to use your first one and your third one to actually get another value of t. Okay, so this is one of the approach. Another approach, if let's say you do not want to do two times, then you can see this is plus, this is minus, so you can combine them. So I'm going to show you the way for combine. So basically the idea is just the same lah. So like depends on which one you like to do. Yeah, basically that's the thing. Okay, let me try to use a green color. So when I try to combine my 2 and 3, then what I can get is, this is all. So the first one is, I mean, obviously it will be easy that you straight away use this. So if let's say you want to combine that, what you can try to do is that maybe your working is a bit shorter, that so meaning that T cos 60 will be equal to 25 sine 20. Then after that, one is plus and then one is minus. Okay, then after that 0.3r. So this is like our fourth equation here. So after I get my fourth equation, then I use my first equation to substitute into my fourth equation. So number 1, substitute into number 5. So I have T cos 60 is equal to 25 sine 20 plus minus 0.3. So my R is 25 cos 20 cos 20 minus T sine 60. Okay, am I right? So T sine 60, yeah. Okay, so after I substitute, then I will straight away solve it here. So which means I do not need to do 2 times. So I can straight away do this 1 time. So which means what I have is, let me try to expand it first. So 60 equal to 25 sine 20. Okay, so the plus minus here will just be the same, right? When you try to expand this part, so 0.3 times 25, and I think you can get 7.5. So 7.5 cos 20. So this is the part that you need to be a bit careful. So this is plus minus. So when you multiply with minus, right? What happened here is plus minus become minus, right? then minus minus become plus. So that's why this will be, I mean, upside down. So which means when I try to do plus later, it should be continue to minus. So that's why I say this is a bit tricky to combine it like this, but this is an alternative so that you don't need to do two times. Then 0.3 t sine 60. Okay, so now we want to group the t together, right? So this is minus plus. So when you move, so okay, let me try to write like this: t cos 60. So we want to group the t part together. So this is minus, right? When you move to your left hand side, then it can become plus. This is plus. When you move towards the left hand side, it become minus. Then after that, 0.3 t sine 60. Okay, then it will be equal to 25. So this is still the same. Plus minus 7.5 cos 20. Okay, so now we can take out our t. So to find our t, then it will be equal to 25 sine 20 plus minus 7.5 cos 20, and then over cos 60, and also it's plus minus because I'm moving to the other side, then it becomes divide only, so the sign doesn't change. So you can imagine as if let's say this is plus, you move that, it's also plus, right? This is minus, you move over the other side, also plus. It's minus, sorry. Okay, so you can use your calculator to press your first time, which by using plus, then after that you use minus, then you solve the other one. So you'll be able to get your two answer is 20.5 Newton in three significant figure and 6.26 in three significant figure. Okay, so when we are trying to put this back to the equation, right? So what we realize here is, okay, this is the part where okay, let's try to label it. So this is the part where we try to say the friction is moving up, right? So which means this is the one that preventing it to sloping down. So this is like the minimum tension that we have. So after that, this is like the maximum T. So you can try to look at the answer and see. So when we try to combine them together, we are writing the plus and then minus, right? So maximum and then minimum. So which means at the end when you try to solve it, so the plus one is giving you the maximum answer. So the 20.5 is basically from the plus one. So which know is correct. Then after that, 6.26 is going to give you the minimum. So that's why this number should be lesser than this answer. Okay, so when you try to look at this one, so it's the same thing. When you use 1 and 2 to solve, it will actually give you a minimum value first, then after that it will give you a maximum value. So which means if you are using this method, so the first one you should be getting 6.26, then the second one you will be getting 20.5. Okay, so that's just a difference between the maximum and the minimum. So you can see the difference idea is just that when I try to apply the minimum force, I'm just trying to apply it from sloping down. So the other case, which is now I have like so much, you can see there's so much space between your answer is like 20.5 to 6.26. So what I'm trying to do here is that the object is still in equilibrium. It's just that I can exert a minimum T so that it's in equilibrium, that it didn't slip down. Okay, then the other point is I want to exert the maximum T so that it's the maximum number, but then it's still not enough for me to actually pull it and then to actually cause it slide up the slope. Okay, so this is like the idea of these two answers. So I hope that you can understand the idea, and yeah, so spend some time to understand it, then you will actually have this kind of question in your exercise also. So let me know if you have any questions. So that's it for today's lesson. Thank you.